Electrical system power quality. In this presentation, we're going to be looking at what is power quality, types of power quality disturbances, effects of poor power quality, tools for measuring and evaluating power quality, and methods of preventing or minimizing power quality disturbances. Power quality is really a subjective term. It's used to describe the quality of the electrical power supplied to a specific application. Power systems vary significantly. Some systems are strong, quote unquote, with significant nearby generation. Others are weak with limited nearby generation, while some are simply isolated with only site-provided generation. Regardless of the type of system, the quality of electrical power is always an issue. The basic components that define power quality would be the voltage and current waveforms, any waveform distortion, and power availability. First, we're going to look at voltage and current waveforms and waveform distortion. Items that come up may be things such as transient distortion. It's an inconsistency in voltage or current waveform that appears sporadically, sort of like one-time events. So if it's only happening one-time event, it's really difficult to predict what the impact will be on the electrical system. There are preventative methods available to reduce the impact of transients. However, they're used only reactively. And so that's only when we have experienced a failure. If you take a look at the transient shown here, we have significant spikes of voltage. So a transient is a spike of voltage, which causes a spike of current. And this can then lead to damage of conductors and insulation on motor windings and all sorts of other equipment. Flicker distortion is an inconsistency in the voltage or current waveform that happens every few cycles. So what this means is that it's very consistent, and it's something that is difficult for us to quantify and manage. Power availability is the ability of the power source to provide unlimited current as needed without varying the voltage or frequency. There are three main factors when it comes to availability: dips and swells, outages, and unbalance. Let's take a look at each. Dips are very commonly seen in electrical systems. Dips are a temporary decrease in voltage, and there's one way to describe it would be to help boost the effective current supplied. This usually occurs when demand for the current exceeds the supply. And so if we were to overload a transformer, what we would expect is that the voltage would dip. If we have dips for extended periods, power sources may increase their generation or change switching configurations to boost the voltage, or shed some load in order to meet the demands of all the customers. So a dip in voltage is not good. Swells are the opposite. They generally occur less often and usually as a result of a quick decrease in demand. So what this means is we take offline a significant amount of load, and for a brief period of time, the voltage goes up. Load unbalance has to do with load or group of loads within a site that use more power from one phase than another. This leads to an unbalance. Now, this type of imbalance can easily be resolved by simply changing where the loads connect onto each phase. And it may go unnoticed on an electrical system for long periods of time until a motor or another piece of equipment becomes damaged. Outages are probably the one that's easiest for us to recognize, and outages come in short or long-term situations. A short-term outage might be something where we barely even notice that we have had a reduction in voltage, and it's a very short number of cycles that we're without power. A blackout would be a long-term outage, and this has to do with the generation of supply and any loss of generation on the overall power grid. Harmonics. Harmonics are a waveform distortion, and harmonics are waveforms that are introduced onto a power conductor. Harmonic waveforms will distort the supply waveform, which is known as the fundamental frequency. In North America, it's 60 Hz. Harmonics are generated by specific types of electrical loads. Linear loads are old-fashioned, we consider, and they don't use electronics to modify the input of their power. Examples of this would be across-the-line skim motors, uncontrolled lights, so just standard incandescent lights, heaters, things like that. Nonlinear loads use switching electronics, so things like rectifying and inverting circuits, and they only use a portion of the waveform to reduce the quantity of electricity necessary to run a similar linear load. So nonlinear loads cause disturbances. Finally, the last item that we have that can have significant impacts on power quality is improper grounding. This can lead to circulating currents, which cause disruptions to communication equipment. So poor power quality can lead to overheating of conductors and terminations, nuisance tripping of overcurrents, premature motor and capacitor failure, computers, timer, and communication problems, general equipment overheating, and funny enough, higher than line conductor neutral currents. In order to measure and evaluate the go-to type of device that we have for our use in the electrical sector these days is called the Power Quality Analyzer, or PQA for short. This is a portable handheld device that's able to analyze any number of different factors that we have seen in some of the previous diagrams. They can monitor every phase of a three-phase system simultaneously. They can record and save data of electrical system operation over a prolonged period. They provide phasor diagrams, bar graph, power factor, power values of everything in the system. They can even measure harmonics. And often they can be left connected to a system for a prolonged amount of time and then retrieved, and the data that was recorded analyzed to figure out what was happening when the voltage sagged or what was happening when the harmonic increased. Now, these items aren't exactly cheap, but they are simply a go-to item when troubleshooting gremlins in the electrical system that don't seem to have any obvious cause. A typical PQA comes with 4 current loops or current clamps and 4 voltage probes or voltage clamps. And in this way, it acts as 4 simultaneous current and voltage meters and able to monitor and calculate every known value for the circuit. Here's an example of a menu for such an item: dips and swells, harmonics, power and energy loss calculator. A lot of them even have power inverter efficiency, so we can hook it up to an inverter and see how efficient it is. Unbalanced inrush, so how many amps is the motor drawing at inrush? And then just generally volts, amps, and hertz. So here's one of the real-time phasor analyzer views, which looks very similar to a piece of lab equipment that you may have used while in apprenticeship training. Real-time peak, RMS, hertz, and something called CF, which we'll discuss in a few minutes. Real-time kilowatts, kVARs, VA, and power factor. And finally, sort of long-term recorded events. So this is long-term voltage recorded events. And what we can do is determine at what time did the voltage spike or sag occur and what loads are being turned on at that time or turned off. Harmonics can be quantified one of two ways: a calculated ratio called the system's crest factor, abbreviated as CF. And this is the peak value divided by the RMS value. Another way we can do this is with a percent called the system's total harmonic distortion, or percent THD. And this isn't a simple calculation, but one that takes into account all the different harmonics that may be present on the line and sums it up as a nice clean percentage for us. The way that we determine crest factor is by comparing it against what a standard or no harmonic system would look like. So a non-harmonic system for a 120 volt AC system would be a 170 volt peak divided by 120 volt RMS, giving us 1.41 crest factor. That would be standard. A poor crest factor, where there are harmonics present, would be when we measure a peak value of voltage of 300 and the RMS at 120, giving us a CF of 2.5. Now, all this is doing is attempting to quantify in a numeric value to indicate to us the uh, magnitude of harmonics that are present on the line. We can see here a crest factor of 1.43, 2.39, and 4.68. And as the number increases, the distortion on the overall fundamental sine wave is significant. Again, another display on a PQA indicating the distortion of waveform and the crest factor associated with it. THD is probably a more common application these days, and percent THD is more accurate because harmonics come in various numeric values. Now, the third, sixth, and ninth harmonics are often considered to be the worst, quote unquote. However, on a percent THD scale, it will actually take into account typically 30 harmonics that may be present and quantify them as an overall percent. The higher the percent THD, the more harmonics are present and the worse the system is. Again, we can do recorded harmonic events over a time period and try to establish or pinpoint what was happening in the surrounding industrial environment that would have caused these harmonics to be increased or reduced, or perhaps there was no change at all. An interesting item that comes along with harmonics is neutral conductor currents. So the third and ninth, sometimes referred to as zero sequence or triplins, add in the neutral conductor rather than cancel. This is rather bizarre, and the dotted line that's shown that bisects the phase A, B, and C current sine waves is showing that on all three phases, the harmonic that has been developed is at its peak. And what that means is that there is now going to be a larger current value on the neutral conductor. They're not going to cancel. And so because of this, if there are harmonics present in a system, often what we will do is increase the size of the neutral instead of downsizing. And the reason for that is to try to accommodate the increased value of current. There's a number of different methods of preventing or minimizing power disturbances. We can fix the problem causing the poor power quality. We can condition the power with specialty equipment. We can use standard delta Y transformers, and we can install equipment that's able to handle harmonic disturbances. So first off, correct the problem. Well, this only goes so far. Tightening lugs, reducing nonlinear loads that may not really be feasible, balance the load across phases, that certainly is something we can do, and ensure proper grounding, definitely. But it doesn't take into account all of the different power quality issues that we've talked about in this presentation. So it really has limited ability to correct the problem. The other option we have is to use specialized equipment to condition the power. And often these are rather expensive devices that take into account what type of disturbance is present on the line and artificially manipulates it to try to cancel out the effects. There's a number of different types of conditioning equipment on the electrical in the electrical field, and we're not going to go into the details as to how and why and what types, as it really is dependent on the type of problem we're encountering. Another alternative is to use something called an uninterruptible power supply, or UPS. Now, this doesn't solve every problem, but it does help to prevent loads from being under voltaged or over voltaged, or even brown and blackout situations because it utilizes a battery bank. Again, we're not going into significant depth on UPS systems in this presentation. Simply put, a UPS system is able to provide constant power to a given load. Another option is to install delta Y isolation type transformers. Now, why would we use a delta Y isolation transformer? Well, this really is only a useful type of mitigation step if we're dealing with harmonics. The reason for that is a delta Y transformer will shift the phase voltages by 30 degrees. And this 30-degree shift, not all the time, but very often, prevents harmonics rather from being transmitted along the electrical system to another separately derived system. So the harmonics could be on the left side here on the delta side, and on the Y side, we have now prevented the harmonics from passing through. On the other hand, we could do it the complete opposite way. We could go this way, in on the Y and out on the delta. It doesn't really matter which side is coming in and going out. All that matters is that we have a phase shift of 30 degrees, which is a fairly cost-effective measure in order to reduce or prevent the transmission of harmonics. Even if the load does not require a change in voltage, a 1-to-1 voltage ratio delta Y transformer can be used. In this way, we can prevent harmonics from interfering with sensitive electronic devices if we know that there are harmonics on the main supply line. Or we can utilize a delta Y transformer to prevent harmonics coming from a known harmonic generating load from progressing through and upstream to the larger power distribution. Finally, we could install larger equipment that can handle the increased stresses from the harmonics. So let's say we have a delta-delta transformer and it has been spec'd in the job. Well, we know that harmonics are going to increase the current value and the heating and all of that. So that means really what we could do is just install a larger kVA transformer than what is necessary for the load. We're not actually trying to prevent the harmonics in this situation. All we're doing is upsizing the equipment to better handle the stresses. Now, standard isolation transformer, as we've already said, 30-degree phase shift from delta to Y. And on the other hand, we could get a K-factor transformer, which is simply a transformer that has been designed specifically to better handle harmonic disturbances. It's pretty much the equivalent of a oversized transformer, but it's got some specific design features that make it a little bit better suited for handling those increased disturbances that we see in the fundamental sine wave. And we can see listed here the K factor, and it says there is a numeric value there. This isn't something that we have to memorize, but simply know that the K factor is a numeric value given on a transformer, K1 being the very lowest, so least ability to handle harmonic or nonlinear loads, and the highest numeric value, K20, would be something that can handle significant nonlinear or harmonic disturbances without sustaining damage.